In this video, I'm going to be describing population growth. We're going to be using a continuously compounded equation. So if you haven't watched videos talking about the Euler number or compound interest, you might want to watch those first just to get a better idea of how to solve these problems and how to use these equations. So the population growth formula is the exact same as the formula for a compounded interest continuously, because populations are growing continuously, especially examples like insects, fruit flies, rabbits, things that reproduce very quickly. Their growth is a very continuous and fast growth. So what we do is we end up using this equation where P stands for our initial population. Because it's growing continuously, we're going to use the number E, and we're going to raise it always to the rate of increase times the amount of years or the amount of time passed. We're going to multiply those together, and that's what we're going to raise E to that power. So we can think of it as a function, and we could call it a function. Or you can think of this as just your output or your answer. So I'm going to use an example of fruit fly growth, population growth there, because they are very quickly reproducing. Let's say that you spend some time doing an experiment where you have a number of fruit flies in a jar, and you are calculating how fast they reproduce and how fast their population grows. Let's say that you do that and you come up with this equation to represent that information. We're going to use this example just to talk about what each value represents here. T is going to represent the amount of time passed. So if no time has passed, we're going to insert a 0 in there, and that's going to give us our initial population, what we start with at the very beginning before the clock starts. So if I substitute in this formula, if I substitute 0 for t, well then all the exponent becomes a 0, and e to the 0 power is 1, anything to the 0 power is 1, and then 20 times 1 is just 20. So mathematically that's how we can show that our initial population was just 20. We just started with 20 fruit flies. And now the clock has started. So our rate of growth is always given as usually a percentage, but when we substitute it or input it into our formula, we always want to input it as a decimal form. So I'm just asking you, what is 0.03 as a percentage? Hopefully you know it's just 3%. Just move the decimal point 2 spots to the right, or multiply by 100 to convert it to a percentage. You would move the decimal point 2 spots to the left if you wanted to convert it back to a decimal, or divide by 100. So hopefully you know how to do that. Alright, now we've gotten into our experiment. A couple of days have gone by, and we notice a bunch of fruit flies hovering over our fruit compost. So we're going to try and figure out what would their population growth be after 24 hours if we just didn't take the trash out for a day, or if we forgot to take the trash out or ignored it for 3 days, then how many fruit flies would be hovering in our kitchen or our lab or wherever we're at here. So let's use our equation, same equation. We came up with it. It was given to us. 20e to the 0.03 times t hours. So this time t represents the amount of time that has gone by. So if 24 hours have gone by, we substitute 24 instead of t. We can use our calculators to do this fancy math. If you have a scientific calculator or a graphing calculator, you simply press the E button and then raise it to this power. It can do the math all for you. If you don't, you're going to have to use 2.0 178 instead of e and raise that to this power and multiply by 20. If you're able to do that, you should get approximately, and it'll be a decimal. You can always round since we're talking about actual things, actual fruit flies. Let's round it to about 41 fruit flies are existing after 24 hours. So we went from 20 initial fruit flies, we basically doubled it within 24 hours. So they grow or reproduce rather quickly here. If we sit on it and we wait for 3 days, then how many fruit flies do we have hovering in our room? So the only thing we're going to change in our formula is just that t value. Instead of 24, we're going to substitute 72. Let's do the math all over again. Pause the video if you want to do it yourself, or just follow along here. Trust that you get approximately 173 fruit flies after 3 days of it just sitting there. If we continue to let it sit, this population is going to grow exponentially. So it's going to get very big rather quickly. And that is the idea of population growth. It happens in humans as well, although we produce a lot slower than that. So our population growth grows a little bit slower. But as our numbers or population increases, that number will increase exponentially just as much. So let's look at a world population of people this time. Doing some research, I discovered that a written report in 1969 was given, and it was in a magazine or a publishing called the National Academy of Sciences, and it was talking about how our world population couldn't be more than 10 billion without our planet and our society going through some degree of discomfort or turmoil or whatever you want to describe here. And that was written in 1969, so by now I think they were onto something, because our actual population is getting close to this, and we are starting to see a lot of resource problems, population problems. So we are experiencing some degree of discomfort, and we are losing some individual choice at the moment, and it probably will only get worse if we continue to reproduce. So let's see what's going on here. At that time in 1969, we were at 3.6 billion people, and it was projected that we were growing at a growth rate of 2% per year. So if we want to write an equation that represents that, we can do the same thing. P is going to represent our initial population, so 3.6 billion. We can leave it as 3.6 as long as we know we're talking about billion. Or you can write out 3,600,000,000 if you really want, but we'll just simplify things for now. It's going to be E always. That's always part of our equation. We're going to raise it to a 2%. So if I write that as a decimal, it's going to be 0.02. And T is going to represent the number of years after our initial stated population. So if we said that in 1969 this was our population, then whatever we substitute for T is going to be the number of years since 1969. So you're going to have to do some subtraction there. Let's try it out here. So if this were the standard population growth, if it had continued in the last 50 years, only growing at 2%, which is not quite accurate, but we'll just use it as an example here. What should our population be right now in the year 2013? Well, we got to figure out how many years since 1969 that is. So if we go up to 70, then we had 41 years since here and 2010. 1 plus 30 is 31, plus another 10 is 41. And we got 3 more here, so that's 44 years since 1969. So instead of T, we substitute 44, and we type it into our calculator, let it do all the math for us, and it gives us approximately, let's see here, punch in the round numbers. 8.68 billion, just approximately. So we're getting quite close to that 10 billion mark if we were growing at a 2% rate of growth. Let's see what would happen 7 years from now. In 2020, what's our number going to be if this many people are reproducing? Well, instead of 44, we got 7 more years, so we're going to substitute, what is it, 50, 51? That would be 7 more than 44. Punch it into your calculator, and we should get approximately 9.98 billion. There we go. So real close to that 10 billion mark, that tipping point in the year 2020. So it's kind of a bad place to be. Luckily, in the year 2000, a bunch of experts got together and recalculated our population growth. They found that it wasn't quite 2% anymore. We had wised up. We're not populating the Earth quite as quickly now. We're only doing it at about 1.3% growth rate. So a bit better. We're going to survive till 2020 at least. So using that new percentage, we're just basically doing the same math again. In the year 2000, we noticed that we have 6 billion. So we're going to start with a new initial population. We're going to start with, that's ugly. Let me just try that one more time. We're going to start with 6 billion. And we're going to raise it to a different growth rate. Now it's going to be 0.013. And t is going to represent the amount of time since 2000, because that's when we measured our population of 6 billion. So in the year 2020, that's only 20 years later. So we'll substitute 20 in there. Let our calculator do the math. And we get about 7.78 billion people. So a little bit better numbers there. Earth can sustain that a little bit better. But let's see if this continues, if this growth trend continues, what's it going to look like in 2050? So same initial population, same growth rate, but now we are 50 years later since 2000, so 50 instead of t. Let your calculator do all the math for you, and we get approximately 11.5 billion, so well over that 10 billion threshold. Seems that 2050 is going to be some problems if we continue to grow at this 1.3%. So luckily, we'll have some experts get together again in 2020 and hopefully come up with a much slower growth rate there, and hopefully the population of this planet wises up and really realizes that we can't grow, we can't continue to populate this planet at the rate that we're doing it and sustain ourselves. We're going to run into a lot of troubles with resources, land, and yeah, there's going to be some problems there. So good luck playing around with population growth trends using just that formula, just this initial continuously growing function or formula there.